In 1948, Dutch physicist Hendrik Casimir predicted that two metal plates in space, about a micron apart, isolated from any type of matter, would strangely attract. This phenomenon is now known as the Casimir Effect. But why do the plates attract? Well, to answer this, we must first understand a bit of quantum electrodynamics. Developed by English physicist Paul Dirac, quantum electrodynamics, or QED, is a specific type of quantum field theory, or QFT, that describes electromagnetic interactions through the electromagnetic field. At every point on the EM field, Dirac imagined an oscillating spring, which he called the quantum harmonic oscillator. These oscillating springs would manifest themselves to us as photons. Dirac also proved that these springs can oscillate with a minimum amount of energy equal to the reduced Planck constant times the angular frequency of the oscillation divided by 2. Any larger amplitude than this value would have to be an integer multiple of that minimum energy. If we were to examine a part of the universe which was isolated from any type of matter, we would see many of these springs oscillating with this minimum amount of energy. See, the vacuum of space isn't entirely a vacuum. It actually has many particles popping in and out of existence almost instantaneously. These particles are known as virtual particles. With no other interactions taking place aside from virtual photons appearing and disappearing, the vacuum is at its lowest energy state, known as zero-point energy. Just as these minute oscillations in the EM field would result in virtual photons, oscillations in the electron field or gluon field would result in virtual electrons or gluons. In the early days of QED, virtual particles were just an approximation tool to get around a lot of difficult math. For instance, electron repulsion is extremely difficult to describe through QED, so instead, physicists described this repulsion as a simple photon exchange between the electrons. So the electromagnetic repulsion between two electrons can be thought of as just the conservation of momentum. But, believe it or not, the Casimir effect actually gives us evidence that virtual particles are real and not just mathematical constructs. See, around the two plates, there are virtual photons appearing and disappearing constantly. However, the tiny space between the plates restricts the EM field to create standing waves of light. Now clearly, more wavelengths of light are being created on the outside than on the inside. This creates a pressure being exerted by the outside photons, which means that the plates must come together.